So now our second talk will be given by Dana Anderson. Dana is the Chief Technology Officer of ColdQuanta and co-founder as well as CEO previously of ColdQuanta. Dana is currently also a professor of physics at University of Colorado at Boulder since 1995. Dana will be talking about Matterwaves, Matterons, and Atomtronic's Transistor Oscillator. Please welcome Dana, everyone.
Thank you, Yunyi. It's a pleasure to be here. It's a pleasure to be part of the first QSC summer school. And what I'm talking about today is mostly work, mostly theoretical work or based on experimental work done at the University of Colorado. However, within the work that ColdQuanta is doing at the QSC, we intend to make the experiments needed to realize some of the things I'll be talking about today on the cloud, so that one will be able to do their own matter wave and transistor experiments. So it's quite a difference in the collection of things that most people are paying attention to these days in quantum technology. This is a rather different stream. Although there is an Atomtronics annual meeting this year in July, which is free, in June, which is free. And if you remind me and send me an email, I'll send you an invitation to that because they don't charge for it. So Atomtronics, it's a faithful analog of electronics, and you can be essentially immediately familiar with it to the extent that you're also familiar with electronics. So an atom flux substitutes for electric current. So you can imagine having some source of atoms, some waveguide or some other thing that confines the atoms, and something that they sync, maybe a detector, and there's a flow, simple enough. And you have particles per second or mass per second as the atom flux, substituting for electric current. And in place of electric potential is chemical potential. So you know what electric potential is. You have a battery. That battery drives a current through a load, written as Z sub L here. And the job of the battery is to keep its terminal voltage, VT here, the same, nominally independent of the load. That more or less is what defines a battery, providing electric potential which drives the circuit. Well, likewise, if we're going to have an Atomtronic circuit, then we think of having some chemical potential source, some load for atomic current to flow through, and the job of a chemical potential battery is to maintain the chemical potential between its terminals. Therefore, the analogy is really good, very faithful, and therefore every function that one knows how to achieve with electronic circuits should also be achievable with these Atomtronic circuits, because the analogy is so good. So why is this interesting, and why do I spend time doing it? Well, in conventional electronics, we know it's hard to work in the quantum domain unless we go to superconductors. But in room temperature circuits anyway, quantum coherence is extremely short-lived. Circuits are coupled strongly to the environment, and one has classical signal currents. In Atomtronics, the goal is to take advantage of very long coherence times, milliseconds to seconds, circuits that are isolated from the environment. And I'm, by the way, not talking about the term circuits as it's used in quantum computing, but the term circuits as it is used in electrical engineering. So we can have circuits that are entirely isolated from the environment, and we can carry signal currents that are quantum in nature. So we can consider superposition, entanglement, and yada, yada, yada in the case of Atomtronics. Now, this talk mostly focuses on an Atomtronic transistor-driven oscillator. I'll get to what a transistor is to remind you, because that will be new for many of you. Old but new. You've got 12 billion of them if you own an iPhone, but you may have never bothered to open it up and see the 12 billion yourself. So a transistor is defined by three regions, typically or three terminals, a source, gate, and a drain for a FET, or a collector, emitter, and a base for the case of a bipolar transistor. In our case, a transistor region is defined by an atomic energy potential, which is shown here in green. And there's a big source region. There are two barriers that define a middle region, a gate. There's a gate width, and this source here, I'm not sure if you can see my mouse. Let me see if this will let me annotate. Indeed, it seems to. So this source, hope you can see my laser pointer, is on a high potential bias. So this is, thank you. This is potential energy, this is position, and the source is at a bias, and the drain is at, we'll just call it 0. So the source is filled with atoms at a predetermined temperature and chemical potential. By the way, feel free to interrupt me with questions. And let me emphasize again, I did it at a very high level, give you what I call the SOF factor. Well, I'm an applied physicist. I like to do things that will eventually be useful. So let me try to describe the SOF factor in Atomtronics. So first of all, in principle, it provides a device that can be used to generate, amplify, and otherwise control matter waves. And what we'll see here is that there's gain present in our systems, and that the mechanism of gain is very different than many of the quantum things that we're used to, at least in quantum optics, like stimulated emission, parametric gain, four-wave mixing gain. This is different. And this also enables a true matter wave analog to the laser. A laser, a CW laser, puts out a continuous, roughly, if you want to call it a coherent state, it somewhat approximates to a coherent state, a continuous stream of photons that are coherent as an electromagnetic wave. And so in the long run, for quantum, and for a variety of things, particularly having to do with sensing, perhaps the transistor based on atoms will be as generically useful as the electronic transistor. As I said, your iPhone has 18 billion. More transistors have been produced than anything else produced by humankind. About Avogadro's number of transistors have been manufactured, an unbelievable number. So again, a device that can be used to generate, amplify, and otherwise control matter waves, an entirely different gain mechanism, and a true analog to the laser. So for those of you who were born post 1980 or so, just to give you a little bit of history and what a transistor is. So this was the replica of the very first transistor invented at Bell Laboratories. It's a three-terminal device in which a small voltage or weak current controls a large current, hence the gain. A modulated weak current will modulate a large current. And there are generically two types of transistors that are familiar. There's the bipolar and the FET, and we use nomenclature that follows the FET. As I said, an incredible number of transistors in manufacture. This slide is already old, before the iPhone 10, I think. So over about an Avogadro's number of transistors have been produced. So if you know how to make a transistor and you know electronics and you can get gain, now we know how to build an amplifier. Now we know how to make an oscillator, a switch, a memory, carry out logic. From there, in principle, we could make radio wave, a radio, Wi-Fi, and so on. A little bit fanciful, but the ability to provide gain is what has brought such power to the transistor.
Hi, Daniel. Sorry for interrupting you. So we got a quick question. So
Sure.
The Fermi-Dirac distribution plays an important role in traditional electronic transistor. So is there anything that similar role for Atomtronic transistor that would be important here? For
it depends on which part that you like. the answer is the analog is very good, and I haven't even worried about so far whether my particles are fermion or bosons. Among other things, the fermionic distribution does at room temperature is give you a finite number of carriers in the conduction band. And for classical electronics, that's the main thing. And we will see the equivalent here, especially if you remind me. But we happen to be using bosons.
Thank you.
So what I've drawn here is a very classic transistor oscillator. And what we know about an electronic oscillator is if we appropriately hook an antenna to it, which I've shown to the right here, to couple the oscillator circuit to the vacuum, to electromagnetic vacuum, I'll emit an electromagnetic wave. And what makes one think twice, and sometimes why we decide to call the current quantum era quantum 2.0, what's rather fascinating is that this quantum state of an electromagnetic field that is a coherent state, excited by connecting an antenna to an oscillator, is the fact that the current clearly in the oscillator is classical. And that's what this chapter in Scully and Zuberi is all about, radiation from a classical current. Very interesting chapter. The point is for us that if we make an oscillator and we somehow couple its output to the vacuum, we generate an electromagnetic wave. In the case of a transistor oscillator, we will see the generation of a matter wave in our case. Okay, so the class of oscillator that we deal with is called the driven oscillator. A child on a swing, which the parent pushes, is called a forced oscillator. A driven oscillator is more like a grandfather's clock, and every driven oscillator has the same ingredients. One, it has gain. It has a frequency selective element. There's feedback, and there's a power supply. Energy comes from somewhere. And finally, there's coupling to the vacuum in the case of what I've shown. And all of these things are shown in the electronic circuit. So gain is the transistor. The resistors are for biasing it. That's all in blue. The frequency tuned element here is, oh, you can't see the color. How about that? Yeah. Okay, there we go. There's the gain element. There's the frequency selective element. In orange is feedback. In red is the battery. Those are the key elements. And as I said, an electromagnetic wave when we couple it to the vacuum. It's really the same principles as a laser, where I have a gain that's atomic atoms with an atomic inversion. Feedback is provided by mirrors, as is the frequency selective element. And the battery is something that keeps exciting the atoms forever, whether it's electric discharge, flash lamp, or what have you. All right. And finally, the laser also puts out an electromagnetic wave, just as the transistor oscillator. Well, we'll be doing something which is analogous. The gain is going to turn out to be provided by a Bose condensate that develops in the gate well. We'll talk about that. It is a harmonic potential we'll see in the gate well. So that's the resonant circuit. There's feedback provided by these barriers. And finally, the battery is actually the condensate in the gate, and this will emit a matter wave. It's going to be the same thing. No reason you should have ever seen this before or understand it yet. But now let me scale you a bit. So in this talk, essentially all energies, unless I forget, are going to be in frequency units, and those frequency units will be kilohertz. So particle energies, chemical potential energies, and so on. Well, the relationship between frequency and energy is just E over H, where H is Planck's constant. So thermal energies, they're given by kBT divided by H. Now we get the thermal energies in hertz or kilohertz. For rubidium, a temperature of 50 nanokelvin, that's pretty cold, is about a kilohertz, a very nice number to remember. 50 kilohertz temperature for a cloud of rubidium atoms corresponds, what did I say, 50 nanokelvin temperature corresponds to an energy of 1 kilohertz. And a 1 kilohertz particle energy is associated with the de Broglie wavelength of about 1.5 microns, all right? More or less a typical communications frequency. A 10 kilohertz particle energy, which we'll also be talking about, is the wavelength of blue light. And therefore, what we'll refer to low frequency electronics, atomtronics, excuse me, of about 10 kilohertz and 1 kilohertz and so on, its behavior and its physics is much more like the behavior and physics of microwave electronics than it is with the circuits that many of us are used to building, say, something that amplifies the room light with a photodiode detector and so on. That's at 60 hertz and so on, or 120 hertz. So we're talking about wavelengths that tend to be short compared to the length scales involved in the system. So just remember that we're dealing with kilohertz, about 50 nanokelvin, and typically we'll be talking about kilohertz to tens of kilohertz energies in this description. Okay? So we'll make very good use of equivalent circuits, such as something I might draw like this one, with a battery, with a bias potential, and so on. But it is important to keep in mind that, again, the wavelength is on the order of and shorter than the characteristic physical sizes. So one wants to be a little bit careful as you think about equivalent circuits when we see them. And it means, for example, when I draw a resistor, like it says RINT, that's R internal, those resistances are distributed, and inductances and capacitance are really distributed when I draw them, not really bulk elements like you might build in a typical undergraduate lab experiment. Okay, so now let's get started. It's sort of an overview till now. Let's talk about Bose condensates. And if this was a real, genuine classroom, I'd look up and I would say, how many of you know what a Bose condensate is and know how they're made? And then I'd get a number of hands in the room. That's a little bit hard here. So forgive me. I'm going to start from scratch, more or less. So I told you that circuits are powered by batteries, and the case of electric potential is replaced by chemical potential. And if you're like me, when I first ran into it, I didn't know what chemical potential really was. So it comes out of the internal energy of a thermodynamic system. The change in internal energy is given by the temperature, and the change in entropy, pressure times the change in volume, chemical potential times the change in the number of particles. So the chemical potential is simply the energy required to add a single particle to the system. So I have some system which has a bunch of particles, and I consider how much energy does it cost me, or how much does it change the internal energy if I add one particle to the system. That's the same as a 1.5 volt battery. The 1.5 volts means that an electron has 1.5 volts of energy. So for any finite temperature gas, the chemical potential is negative. However, for a Bose condensed gas, the chemical potential is positive, which means if you want to drive a circuit, the BEC is the battery. That's all it is. It's very exotic to us in many respects, but for our purposes, it's just a battery that powers the circuit because it has positive chemical potential. Okay, so BEC is just the battery. How do we make BEC? Well, we start out with a collection of cold atoms in a bowl, like shown here. They might be at a microkelvin temperature for us, or a couple of microkelvin temperatures. So that's that's several kilohertz. They're held in a magnetic bowl, and the bowl has a finite height here, so the energetic atoms can escape the lip of this bowl, and they're the most energetic ones, carrying more than the average of the thermal energy. Therefore, when they leave and you allow the system to rethermalize, well, it gets colder. All right, the remaining ones are left colder. Now, let's continue cooling by lowering the lip of the wall, because it takes a very long time if the lip is too high for atoms to leave. So we lower the lip and we allow the process to continue. The most energetic atoms can manage to get enough energy to get over the lip of the bowl. They leave with more than average kinetic energy, and therefore the remaining ones are left behind. And we continue to do this, lowering and lowering the lip of the bowl, allowing atoms to evaporate, leaving behind even colder ensemble of atoms, until finally it's so cold that they begin to condense. And that's a Bose-Einstein condensate. And that condensate is an ensemble of atoms embodying a single atomic wave function, rather than an ensemble of atoms, which I can think of as individual atoms. Now, typically some thermal atoms remain too, so when I'm done, I have a temperature and chemical potential that I can associate with this ensemble of atoms, and that's going to form our battery. Just in case there are any questions, now's a great time to ask. But if not, I'll continue.
Oh, good. Yeah, there's none. Thank you.
Okay. All right. Now, we make our circuits experimentally using what are called painted optical potentials, work that, and the name of which came out of Los Alamos in the group of Malcolm Bougier. And we make these potentials with a combination of magnetic fields, and the painted potential part is blue detuned laser beams. And so the blue detuned laser beams are what we use to cause a bias and cause the potential to change. Now, let me go in a little bit more detail about what this potential looks like. I've already said it once, but to go in a little bit more detail, 3 regions: a broad source region, FET nomenclature. So we say source, gate, and drain. Source has the battery. The drain is just coupled to the vacuum. And the source well is biased, as I said, with a large blue detuned laser beam that sweeps over, lifting up the atomic potential. And these 2 barriers, as I said, are formed by blue detuned laser beams, but we carefully shape things so that the quantized energy level of the gate are approximately equally spaced, meaning that the gate well looks like a harmonic oscillator, at least when you have low enough energy. And there's a specific reason why these 2 barrier heights are different, with the second one, the one on the right, being taller than the first, but I'm not going to go into that today unless somebody really makes me later. We call these last 2 levels the transistor modes of the system, because the tunneling through these barriers is large enough only at the very tip of these barriers to couple the gate to... Question? No, okay. To couple the gate to the source and drain wells. So this is our model, is we have a broad source well with lots of levels, drain has an infinite number, the gate are harmonic until you get the very last 2, and we're called those the transistor modes. All right, so just labeling a little bit more carefully, we call the upper mode the source drain mode and the lower mode the source gate mode. All right, just for the sake of nomenclature. And our battery is the source being loaded with atoms at a specific chemical potential and temperature. Now, if I look back at the transistor oscillator I had earlier, well, all of you pretty much know what this is, but if you're electrical engineers and not quantum engineers, then you would say, well, what is your LC circuit? Well, that's replaced by the quantum mechanical harmonic oscillator of the gate well. It has equally spaced levels like so. And the ground state energy is a half h bar omega, where omega is the classical oscillation frequency. The wave functions are characterized by Hermite Gaussians. Many of you know this. This is a summer school, however, so I'm not assuming that all of you know it. And the various energy levels are labeled with a ket n, known as Fock states. And instead of the usual dynamical equations that I'm used to classically, instead, this problem is typically used to introduce operators, raising and lowering operators in particular. So I have energy levels n. I have the energy of these levels are equally spaced, beginning with a half h bar omega for the lowest one. And then I introduce ladder operators. And today, for those of you who say, okay, I know this already, I need to make a distinction, so I'm being careful. I'm calling ladder operators associated with the single particle harmonic oscillator A and A dagger. And you know that I can raise one level by operating on the state with A dagger, or lower by one level by operating on the state, the Fock state, with A, the annihilation, the lowering operator, and then I get the particle to go to the lower state, upper state with A dagger, lower state with the lowering operator. All right. And a coherent state, and again, I want to be I'm going over this partly because of nomenclature, which can be confusing in our transistor oscillator system. So a coherent state in the harmonic oscillator sense is a state whose time evolution is such that the shape does not change. It just oscillates back and forth in the oscillator. It has a very well-defined form. It's also, its definition is the eigenstate of the lowering operator. So the lowering operator operated on a coherent state is given by the eigenvalue alpha times that coherent state, and it's a superposition of Fock states. You don't need to know this detail, but important to us is that it's not an energy eigenstate. It has a mean expected value for the energy, but it is not an eigenstate. However, it is a quantum mechanical pure state. All right, we're talking about a transistor which has a gate well, which has a finite number of energy levels. So I introduced something I call a truncated coherent state. So there are a finite number of levels, and basically it's the ordinary coherent state up to a finite number of levels n, and I have to renormalize appropriately because of the finite number of levels. And of course, it's not quite like a coherent state. For low amplitudes, it is, but at high amplitudes, as you have oscillations so high that it's getting into these upper modes, well, it distorts the mode a bit, and we could go into that, but we're not going to. For our purposes, until we have to, we're just going to think of it as a coherent state. Now, the reason I had to go over those other aspects that many of you will know is because I need to distinguish the language used in manybody physics. So in the case of manybody physics treating an oscillator, so we have lots of particles. So in that case, oops, I forgot the angle there, but a ket is designated by the occupation of each of the energy levels starting from the zeroth, excuse me, let me just call it the first to make things like the first level, second, third, and fourth, and so on. That's how the Fock state is designated. So there are 3 in the first level, lowest level, 3 in the next, 5 in the next, et cetera, et cetera, et cetera. That indicates the state of the system. We have particle operators as opposed to the raising and lowering operators that I referred to as ladder operators. In particle operators, I have just creation and annihilation operators. And if I'm careful today, I will always use creation and annihilation to mean particles and raising and lowering to mean harmonic oscillator changing energy levels. So I use an annihilation operator or a creation operator to move a particle, say, from one state to another, excuse me, I'm sorry, to I said it wrong. I was about to talk about raising and lowering operators. To move a particle, I've got it here in B2, to move a particle into the given state. In this case, I'm going to increase the number of particles in the second state by 1. And so you'll notice that in this second ket down below here, I have 1 extra particle now in the second level. There's nothing so far about particle conservation. If I want to conserve particles, I have to have as many annihilation as creation operators. All right, so I can also destroy a particle, annihilate a particle, and so on. And then there's something called many-body coherent state. And that's different from this harmonic oscillator coherent state I mentioned before. So many-body coherent state means, say, that in one of these levels, I have an uncertain number of particles in that level. And so when I operate the annihilation operator, I get an eigenvalue here called alpha 2, reflecting the fact that the number of atoms in the second state is uncertain, but given that it's an eigenvalue, refer to this as a coherent, many-body coherent state. And because of the confusion, where I showed coherent state before as the eigenstate of the lowering operator, I sometimes refer to that one in the case where there are many atoms in a harmonic oscillator as a massive coherent state, as opposed to a many-body coherent state. So a bit confusing, and you might want to ask if someone is using the word coherent state, what they're meaning by it. All right, here's my BEC again, just the same slide I had before, but I want to get back to the oscillator. To work out the theory of the Atomtronic oscillator, we have an ansatz, which is very, very unusual, unintuitive, and at first seemingly unreasonable. That ansatz says in the gate, a Bose condensate will develop, which we know from experiments that a Bose condensates develop in an initially empty gate, but that Bose condensate will develop in a coherent state of the gate rather than in the ground state. Formally, it's called a displaced ground state. And because the BEC has many atoms, we don't mean a many-body coherent state, we mean a massive coherent state that just oscillates back and forth. And that's the ansatz, and we have to develop a theory which self-consistently supports that ansatz. Now, to do that and to continue with the theory, let me just consider the 2 upper modes. So these are the very 2 upper modes of the gate well. And because my ansatz is that there's an oscillating condensate in the gate, these modes will be coupled much in the same way as a 2-level atom will be coupled by an electromagnetic field. The mechanical interactions, the collisional interactions of atoms that occupy these modes will be such that these 2 modes will be coupled. In other words, the oscillating condensate can cause transitions between these 2 levels. So instead of working with these original modes, we work in the normal modes of the transistors, which are symmetric and antisymmetric combinations of these 2 individual modes. So I draw that here, and now I have 2 modes with these properties instead of the original particle annihilation operators and creation operators. I have creation and annihilation operators for the normal modes. And here in this equation, I've also assumed that these normal modes are excited as coherent states. And just to be explicit, with average mass, or you could, average numbers or expectation value of the number of atoms being given by the square root of this m plus. I could have called it alpha, but because I'm more interested in the number of atoms and so on, and the average number of atoms, I've just labeled this eigenvalue, the coherent state eigenvalue, this way. All right, so these are many body coherent states. The condensate is in a massive coherent state. I know it seems confusion, but it wasn't my fault that the many body folks decided to call their things coherent states. We were first. We meaning in quantum optics. All right, so it's easy to write down the energy of these normal modes when they are unperturbed. And the interesting thing, by the way, this is a side note, is because there's tunneling out in the drain, there's also spontaneous emission. And it's another thing I won't explore for now. But what I'm interested in is the energy of interaction between the condensate and these transistor modes. Whoops, I went too fast, too far. All right, it ends up being a rather complicated expression, which I'm going to simplify right here to say the energy between the condensate in the gate and the transistor modes, that's what's meant by EGT, is given by some constants, excuse me, by some parameters that say, what is the oscillation amplitude of the condensate and how many atoms are in the condensate? That's all this first term is, plus a factor that I'll go into later if I need to, times the population difference between, for our practical purposes, the number of atoms in the symmetric minus the number of atoms in the antisymmetric mode times this cosine function. And this cosine function is the relative phase between the oscillating condensate, which has a well-defined frequency, and I can think of it as having a well-defined phase, and something that's in the very definition of a symmetric or an antisymmetric mode, meaning that it oscillates either in phase or out of phase nominally with the condensate by definition. By the way, this coupling coefficient alpha, chi of alpha times alpha, as a function of the amplitude of the condensate for a fixed depth of the harmonic potential, it's approximately linear, and then it just saturates. And that turns out to give us the oscillation amplitude of our oscillator later. Again, I'm not going to hang out with that discussion until we need to. All right, but the main point is the bigger the oscillation in general, the stronger the coupling until it saturates at some maximum value. All right, so the coupling energy I'm going to write this way. It's just a rewriting of the previous equation. And this coupling energy can be zero if there are no atoms in the gate. That means mg is zero. There are equal populations in the two normal modes, so this is zero. Or the relative angle between the oscillation of the condensate and the normal modes is pi over 2, that is cosine phi is 0. The interesting thing happens when I start out by assuming that only one of these two modes actually exists, and that's going to be proved to be self-consistent. So we're going to only assume one of the normal modes is present in the gate, and we'll show later that self-consistency for the time being, that only the asymmetric mode is in the gate. I could have chosen the symmetric mode. I chose the anti-symmetric mode here. And it turns out that assuming only an anti-symmetric mode is populated, then, so here's this coupling equation again with only one mode. I'm going to rewrite it as V of phi equals minus V naught cosine phi. So just lump all these into a constant for the moment. We see now that we have a phase-dependent atomic potential. And that's very interesting. It's going to be the origin of gain in the system. And the point is, initially with no coupling, no condensate here, the only atoms that made it into the gate had to be exactly at the given harmonic energy level right here or right here. And the only atoms that could tunnel out would have to have exactly this harmonic energy eigenstate to within a very narrow band given by the tunneling. If the tunneling is small, it's extremely narrow band. But now I have a phase-dependent potential, and what does that mean? It means that there's current gain, because atoms that previously were not resonant, were not at one of these energies, can now, because of this phase-dependent potential, enter in the gate, provide, and this is lousy language, provide they enter with the right phase. On the other hand, this is the interesting thing, another thing that I won't go into in this one and only lecture, is that if you assume that there's only one mode in the gate, then what you discover, because of this phase-dependent potential, is that the other one will be reflected. And in electronics, we call this an impedance matching phenomena. The fact that, say, the anti-symmetric mode can manage to get in the gate, provided it enters, so to speak, with the right phase for a given energy, we say that's impedance matched to the gate. The symmetric one in that case will be reflected because it's not resonant. So I'm going to go into a little more detail, because actually this is not much different than what happens, say, with a forced pendulum, but we just don't think about it that way. So let me imagine here is a magnification of the gate well, and here's an oscillating condensate. Here's a particle, again, bad picture, but it will do for us for now. Here's a particle that can, in principle, enter the gate. And here's a contour plot, if you like, a top view of the potential energy. So you see this dark region in here is the gate, the green is all the potential, and so we're looking down on the atomic potential. It kind of looks like this, with essentially very broad source, infinitely broad gate, and I'm going to allow the condensate to oscillate. And then I'm going to think of particle entering at different times, meaning different synchrony with the condensate. And look, you can kind of see it. If you come in with the condensate is moving to the right from the left, you're kind of moving with the condensate. The interaction energy is going to be less, for example, than if the condensate is moving towards the left when a particle is coming into the right. You can see intuitively that the coupling energy, that the collisions are going to be larger, and the coupling energy is going to be larger. So depending on the exact timing of the entering particle, it witnesses different coupling interactions. And therefore, for example, I'm going to show it here in animation, I have energy less than, suppose I have a particle coming in with less than the resonant tunneling energy, equal to the resonant tunneling energy, or greater than tunneling energy. They can still enter the gate, provided that they do so with the right phase. All right, and that's because, for example, the one that's moving 90 degrees out of phase actually has no net interaction energy. That's the cosine phi is 0. On the other hand, you'll notice that this guy, let's see if I can do it right. This guy is kind of moving with the condensate, the one on the top, and the one on the bottom is moving against the condensate. So if the particle comes in with too much energy, it can give up some of that energy to the interaction energy. On the other hand, if it comes in with too little energy, it can borrow some, so to speak, from the condensate helping to push on it. And this is the origin of gain. So the fundamental offsets is that the Bose condensate is oscillating. Second assumption is that only one normal mode oscillates. And these two together prove to be self-consistent. We'll get to that later. But the interaction energy allows a broad range of source atoms to enter the gate. Again, because of this phase-dependent potential. So atoms can either borrow or lend energy to the interaction with the BEC. And the way we say it from the electric engineer's point of view, first of all, is one normal mode is impedance matched, the other is anti-matched, and so reflects. And the spectrum of energies of the normal modes is much broader than it would be if there's no interaction with the condensate. And that is what gives rise to gain. All right. Now, I haven't established it, but I'm going to give you a view of it. And it's the following. I had this phase-dependent potential. All right, V of phi is given by cosine of phi. And there's a fixed relationship between the phase of the condensate and the energy of the incoming normal modes. And therefore, if I looked at the particles managing to tunnel out into the drain from the gate, I will notice that their potential energy, their corresponding potential energy, varies in synchrony with the gate. And it's propagating to the right because the particles have energy. And this is therefore a matter wave. That it's coherent and so on, I'm not proving at this statement, at this moment, but I want to go further about this matter wave because it's very interesting and not certainly what I originally would have thought a matter wave would be like. So let's continue, and I want to give you a little bit more physical insight. So remember, here are all the elements of my oscillator. Just a triple well potential, 2 barriers defining a tight gate well. The classical equivalent circuit for the DC portion of the operation is shown here. The circuit is powered by a chemical potential mu B on the left, that's a battery. There's a bias potential over here, VSS, on the source. A battery, every battery, whether, even a perfect battery, has to have an internal resistance. I'm not going to go into that today, but it is a fundamental part, whether it's electronic or atomtronic, that a battery is associated with an internal resistance. And I've represented that here. And here I've written these capacitances. They determine the number of atoms or the mass, simply given by an equation that's very similar to what we see in electronics, where we say the number of particles, in electronics it would be the charge, is given by the chemical potential, electronics that's the battery potential, times the capacitance. So these capacitors determine how much mass or how many particles are in this region of the circuit. And in general, there can be a drop. So here's the source. This is right before the source barrier. This is on the other side of the source barrier. And this is a resistance, which is not a physical one, it's distributed. And finally, there's the gate current that goes into the drain. And I close the loop this way, although the atoms just go on forever. I'm not going to worry about that discussion. It just defines a zero potential by which we can measure relative potentials. All right, so this resistance accounts for the power loss of the atoms going out into the vacuum. So first of all, let's think of no coupling, and let's go back to a very classical picture that we have thermal atoms on the left of these 2 barriers. Here's the source over here. Because they're thermal, and if they're cold enough, it will be noticeable that more atoms enter the lower state, so to speak, than the upper state. On the other hand, the only way they can get to the drain is if they're in the upper state, because here the well is so thick, that's why this barrier is higher, that I can ignore tunneling. So in absence of coupling, I can calculate the current I expect out into the drain. All right. So again, on average, they enter the lower level and exit the upper level, not on average, but mostly. All right. Moreover, anyway, these are just the details. Moreover, if I thought of only particles coming into the lower well, well, each of those is a 50-50 superposition of the 2 normal modes. And therefore, if you think of doing individual measurement in terms of impedance matching, every atom has a 50% probability of being impedance matched and 50% probability of reflecting, or since we're doing quantum mechanics, half the wave function is impedance matched and half of the wave function is reflected, all right, in this normal mode picture. All right, so here's the oscillating condensate. Here comes an atom. The condensate causes coupling between the two modes. The only way it can leave is from the upper state. And so this removes energy from the system as a whole, h bar omega naught per particle. And you can calculate how this takes place and probabilities. And you see that heat is removed from the system because of the current that's induced by the oscillating condensate. And the most important physics of the oscillator is quite simple. Here's the equivalent circuit. I told you that there's cooling because atoms come on, most of the atoms come in a lower state and leave to the drain in the upper state. That means there's cooling. That means the same thing as saying heat is removed. And that means that the dissipation in this resistor is negative. And that means this resistor is negative. So there's the power. Gate source is minus RGS times its current. This is just I squared R. Power loss, but it's negative. And if that seems odd to you, that's the way electronic oscillators are in fact described, is gain is replaced by negative resistance. And so this resistance is negative. Well, if this resistance is negative, that means this potential over here in the gate is actually higher than supplied by the battery. And one can do just a straightforward calculation of what one expects for current gain, first of all, and define a transconductance. That's the way FET transistors are characterized by a transconductance. And so you can actually calculate the gain of this system. All right, it's quite straightforward to do just from this equivalent circuit model. And what I told you before of using Boltzmann statistics and so on associated with the thermal atoms that manage to go from the source into the gate. And there's cooling of the gate, negative resistance. That's the equivalent of gain, by the way. And so as I said, I won't go through the calculation, but as I said, it's really very straightforward to calculate all the circuit device properties in terms of this equivalent circuit. And all of these circuit elements can be calculated starting with the atomic potential, the temperature and chemical potential of the source, and the harmonic oscillator characteristics of the gate, as well as the number of levels in the harmonic oscillator of the gate. And it proves to be self-consistent. We start with the onset that the BEC forms in the displaced ground state of the gate. The oscillating BEC gives rise to a phase-dependent potential. The phase-dependent potential means that one of the two normal modes is excited in transistor states. The other one is never excited macroscopically. A substantial drain current arises due to the interaction energy. The drain current gives rise to cooling of the gate atoms, and that cooling of the gate atoms maintains the atoms in the gate in condensate form rather than melting. And why does this happen? It's because that way the circuit attempts to approach it thermal equilibrium with the maximum efficiency, because there's maximum power dissipation when it oscillates as opposed to when it doesn't. And finally, I've got just a couple more minutes from when I started. We saw that current gain resulted from this phase-dependent potential, very important, and that there's a relationship between the phase and energy of the atoms. That, as I said earlier, is a matter wave. So let me start pretending that I never knew about quantum mechanics, but I somehow had this circuit. I would write down this output as a wave in the first place. And this is a classical wave. And suppose I had this classical wave and I said, well, let me quantize it. First of all, before I quantize it, for electrical engineers, this is quite nice because this wave, I'll call it potential wave, which varies in time, is associated with the current. And potential and current, just like they are in electrical engineering, are related by an impedance. The current is related by the potential divided by the impedance, and the impedance is just 2 pi h bar. That is, it's just Planck's constant. Very nice result. The frequency of this wave is just the gate frequency. That's it. It's just the oscillation of the condensate frequency and the frequency of the harmonic oscillator. The phase velocity, however, the velocity of this wave is determined by this bias potential, what energy these atoms see. So they might travel quite quickly, but their frequency is fixed by the gate frequency. But this wave will exhibit interference, just as a wave should. All right, where that interference is given by more easily the frequency of the wave, so that the time between this point traveling to the mirror to this reflector and back, so this is just a steep potential, and back is exactly 1 over the frequency of the wave. All right, there's power carried by the wave, etc. And now we ask, what is this wave? As I said, if I went back and quantized it, what would I find? First of all, I find that the interference and the characteristic of this wave is not given by the de Broglie characteristics of the atoms. For example, the atoms are moving quite fast because of that potential offset and have a very short de Broglie wavelength compared to the wavelength associated with what I'm calling this potential wave. And the atoms, the power carried by the atom flux itself is actually much more than power carried by this matter wave. And that's again because the atoms get a lot of momentum when they've gone out into the drain and realized the energy, converted the potential energy given by the bias into kinetic energy. They carry a lot of momentum and therefore a lot of power. But in electromagnetics, when we quantize the wave, we invent this thing we call a photon to say, here are the quantization elements. And the matter wave dual of the photon is not the atom. It is something that, for lack of a better word, we've just called Matterons. And that may seem gratuitous to name it, to give it a fancy name, and maybe so, I don't know. But we can make a Matteron detector, which consists of a mass, a big wall, and a mass on a spring whose resonant frequency is equal to the same BEC frequency, harmonic oscillator frequency of the gate well. And if I reflect the Matteron wave, the potential wave, off of this mass spring system, I will detect the Matterons, provided I've matched this spring oscillator frequency, mass spring system, with the BEC frequency, and I will not if they're not matched. So I can make a Matteron detector. This is not an atom detector, and the flow of atoms will simply apply a pressure to this mirror, but not an oscillating potential, which will start to get this thing moving back and forth. All right. Plus, the Matterons will exhibit Poisson statistics, everything we know about the ideal coherent state, to the extent that this matter wave oscillator is also ideal, which it won't be, but to the extent that it is, it'll be very much like a coherent electromagnetic wave. And these Matterons carry momentum, just as photons do, that are determined not by the atomic energy, but by the energy of the harmonic oscillator given by this omega naught. All right, so we've developed a theory of the matter wave transistor oscillator, minimum model with an ansatz, one assumptions, and those two are self-consistent. I've talked about coherent matter waves. We've said that they are not de Broglie waves, but cause us to introduce a particle we call a Matteron that comprise a matter wave and carry a specific packets of momentum, just like the photon, and so on. And let me end it there, just about on time, and maybe even a little room for a quick question.
Thank you, Dana, so much for the fascinating talk on this realm of atomtronics and many beautiful physical pictures that you've drawn here between the traditional electronics and atomtronics and all the way to Matterons. Let me see. So there seems to be no question from the audience yet. Maybe let's give them a couple of seconds And so I guess in the meantime, let me ask one stupid question real quick. So you mentioned spontaneous emission from your BEC transistor. And is there any possibility to have any stimulated emission or a coherent source for Matteron, like a Matteron laser?
Yeah, it is a coherent source. It's the Matteron oscillator. We could call it a laser, but of course the L in laser is light, so that's problematic. And the gain is not from stimulated emission as in the laser is. It's a very different gain mechanism, but yes, it's a CW matter wave oscillator. It's subject to the same spontaneous emission noise that the output of a laser is subjected to. And that's because it's coupled to the vacuum.
Right.
It's not a stupid question. It's a great question. You'll have to keep trying if you want to ask a stupid one.
Thank you. Let's see.
So why don't I thank you again, and you're welcome to email me questions. I'm dana@coldquanta.com.
Yes. Let me check real quick on the, okay, so nothing on the YouTube streaming either. Let me see. Sorry, so maybe one more from me. So you mentioned that the coherent state, the space that you consider is truncated, and is there any non-trivial physical consequence for that? Having
Yeah, I mean, I haven't worked it out, so I don't know for sure, but there's a strong suggestion that actually the state is squeezed. You could see it in the one graph. You could see it was quite narrow. So it prefers to put out a squeeze state, but that's tentative. I don't know about the real dynamics involved and so on.
Thank you so much.
You're welcome. Not surprising because saturation has taken place and often squeezing can be associated with saturating phenomena.
Yeah.
Anyway, you're welcome. And thanks again for having me here, and hope to hear from somebody to ask some good questions.
Thank you, Dana, again for really fascinating talk, and it's really our pleasure to have you here today.